The following video is a recording of a lecture from Genes to Galaxies, the 35th Professor Harry Messel International Science School, presented to high-achieving Year 11 and 12 students from across Australia and 10 other countries.
Well, on to Mars. There's been a fascination with the possibility of life on Mars for a very long time, and indeed there was a time when there were thought to be canals on the surface of Mars. Maybe some of you know that story. But let's start with the context again. Here we go. Now, because I have two screens, I'll do it this way. There, of course, is Mars. And as you can see, it's significantly smaller than the Earth and red-coloured. We'll talk more about that as we go along. And back in the 1880s, an Italian astronomer named Schiaparelli made maps of canals on the surface of Mars. This happens to be a German version, which is why there's some German text there. These canals could only be seen when conditions were absolutely perfect. Astronomers call it the seeing. When the seeing was perfect, Schiaparelli and some other astronomers, including Lowell in the US, could see these canals, but only just occasionally. But they persisted for long enough that they could map the canals on the surface of Mars. And from that grew all sorts of stories about life on Mars and a dying race of people on a drying planet who built these canals to convey water to convey water from the poles to the equator, so they could continue to live in the pleasant conditions near the equator. And in fact, one of the earliest science fiction novels was written about that time in the 1880s, called The War of the Worlds, by H.G. Wells. And a somewhat amusing result of that was in 1938 in the US, that book was serialised in two broadcasts about an invasion from Mars, and it was meant to be a joke, and the first of the serials was played on the eve of Halloween, but the result was a lot of people thought it was serious, and so it was said that there was something of a panic about the invasion from Mars in 1938, and then when it was realised it was a hoax, there was a lot of anger. It's useful to know this background. But if we move on to the 1950s, this was about the best image that we had of Mars, taken from a ground-based telescope, because there had at that stage been no missions to Mars. And interestingly, some astronomers saw in these images evidence that there might be life on Mars in those dark patches on the surface of Mars. That's an icy pole, the North Pole there, by the way. But those dark patches change shape with the seasons. Mars has seasons, like the Earth. And so it was thought that since those patches change shape, then maybe there was seasonal growth and dying of life on the surface of Mars, something like mosses. And that was apparently, astronomers here might correct me, but apparently that was not an unreasonable idea at the time, and had some respectability. So we're still thinking about life on Mars. Let me remind you, though, about this diagram and what we're looking for in terms of life anywhere else in the universe. And you'll hear more about this from Jill Tarter next week in relation to the SETI search, the search for extraterrestrial intelligence. But there's not a great deal of intelligence in life on Earth, as I pointed out to you yesterday. It resides here, and depending on how you like to think about it, maybe with dolphins and a few other animals. But this is our model of life. It's the only one we have. And if we're thinking about searching for life elsewhere, we're not really going to be looking for little green people on Mars, we're going to be looking for something microscopic. That's the lesson we would take from the observation of life on Earth. That doesn't make the search any less profound, as I'll discuss later, but that is the reality of the search. We're looking for microbes on Mars. And so just think about that proposition. We've got a whole planet to search and we're looking for things that are microscopic. That's a challenge. But we think we know how to do it because of what we've learned about looking for microscopic life on Earth, what I discussed with you yesterday. We have the techniques to find evidence of microscopic life on the early Earth, and they're exactly the techniques that are being employed on Mars in particular. We have much better images of Mars these days, of course, because there have been numerous missions to Mars, and there are satellites in orbit around Mars with cameras such as the HiRISE camera on Mars Reconnaissance Orbiter that has a resolution of about, in the favourable circumstances, of 26 centimetres per pixel. So the camera on that satellite, it's essentially derived, I presume, from spy satellite technology, can see objects as small as 26 centimetres on the surface of Mars. It's a marvellous engineering achievement, I think you would agree. In fact, all these missions to Mars as a whole are just mind-boggling in terms of the engineering that's involved in all of them. I'm going to talk to you about the Phoenix. We see the landing site indicated there a little later. That's the most recent mission to Mars. Now, it's very expensive to send missions to Mars. The average cost of the smaller of the missions is about $260 million US dollars, and the more complex missions cost about $1 billion US dollars. You can question whether that you'd like your taxpayers' money spent that way, and I have a number of answers to that question if you'd like to challenge me on that. I would be perfectly happy to spend my taxpayers' dollars on doing this. But there's a cheaper way to look for life on Mars, and that's to wait for Mars to come to us. This is a meteorite that has the romantic name of ALH 84001. It was found in the Allen Hills region of Antarctica in 1984, and it was the first to be catalogued, ALH 84001. And people search for meteorites in Antarctica because they tend to be dark rocks and they're easy to see on the ice. So many hundreds of meteorites have been found in Antarctica and of course in other areas as well. In fact, we know of about, I think, 30,000 meteorites. But of those 30,000, something like 30 are known to have come from Mars, and this is one of them. And how would you know that a lump of black rock, that's about the size, as my US colleagues say, of an Idaho potato, how would you know that it came from Mars? Well, amongst those 30 meteorites are two that have trapped within them samples of the atmosphere of Mars. There are little gas bubbles in them. So a meteorite is blasted off the surface of Mars by the impact of an asteroid, and that provides enough energy to launch a rock into space. But it tends to melt the outer part of the rock at the same time. So as it passes up through the atmosphere of Mars, gases can get trapped within the molten outer rind of the rock, and those gases can be sampled if a meteorite eventually, or that rock eventually makes its way to Earth, as some percentage of them will. The composition of the atmosphere of Mars was measured by NASA's Viking landers in 1976 and 1977 with gas chromatograph and mass spectrometers aboard the landers. And we know from those days what the atmosphere of Mars is made of. It's CO2 and nitrogen and a bit of argon and some other trace gases. And that's exactly the composition that's found in these little bubbles trapped in and two of these 30 meteorites that we now know came from Mars. That's the key piece of evidence. There are other lines of evidence. So here we have a rock from Mars. It's it's much cheaper to go to Antarctica and pick up a few rocks than to go to Mars itself. There was a great deal of excitement back in 1996 when it was announced by NASA and indeed by President Bill Clinton that this rock contained evidence of former life on Mars. Bill Clinton was well advised to say, if this should be proven to be true, it will be one of the greatest discoveries of all time. And that would have been correct. There were 6 lines of evidence that I won't go into here, but I can talk about it if you'd like me to later. All 6 have now been discredited, and as is the nature of science. And so this rock does not contain any evidence of life on Mars. Some of us were sceptical from the beginning, and I'm not saying this with the wisdom of hindsight, but those of us who've looked for evidence of early life on Earth know how difficult it is, and to expect to find that evidence in one random sample of Mars that we just happen to have beggared belief in the first place. I mean, of course, it could have been correct, but I, for one, and many of my colleagues were not at all surprised when it turned out not to be correct. But what did they find? Things such as this, when they broke open little bits of the meteorite and looked at it with a scanning electron microscope, they saw these things such as this. It was described in the press as a worm, but it's only micrometers in size, but it looks like a fossil microbe, like some of the things I showed you yesterday. And they found all these little spheroidal structures, and these were said to be fossil microbes. The problem from the beginning was, and I'll just talk about one line of evidence, was that a lot of these spheroids are only about 20 nanometers in diameter. And the volume of such a spheroid is so small that it's impossible to even fit one protein molecule inside it, let alone all the rest of the biochemical machinery of life as we know it. So that was another reason for scepticism from the beginning. But there was a huge flurry of press interest, of course, which was quite natural. It's all just quietly gone away. So let's talk about missions to Mars. I wonder if you know how many attempted missions there have been to Mars. Would anyone like to have an estimate? How many missions have there been to Mars, or attempted missions? Any idea? Yes, over here. 14? 40. Yes, that's right, 40. We'll interpret that as you having been doing your homework. Very good. Only about 20 missions have made it. And some of them have ended up in the Pacific Ocean or various other places that they weren't intended to go. But most of the recent attempted missions have actually got to Mars. And this is the track of the Phoenix mission. Every 26 months, Mars and Earth are in relative positions such that a low-energy, fast mission to Mars is possible. And there you see the track of the Phoenix mission. It was launched from Earth here, and over a period, I forget how long this was, but probably about 6 months. A little bit longer than 6 months this one was, I think. It arrived at Mars. So this is the orbit of Mars, and this is the orbit of Earth, and there's the Sun. So the missions are planned to take advantage of that opportunity when Earth and Mars are in just the right relative positions. And those 20 missions that have made it have mostly been launched in this configuration. Oh, never mind. Well, what this slide shows is that early on in these missions, dry river valleys were discovered on the surface of Mars. There are abundant dry river valleys, But if we look at... no, the next slide is this one. Yeah, never mind. No, it's okay. Just imagine dry river valleys, okay? Imagine you're looking at Central Australia or Arizona or somewhere like that, or the Atacama Desert. And you can see that once water flowed on the surface of Mars, but not anymore. This is what the surface of Mars looks like now, close up anyway. It's a dry, cold desert. The average temperature on the surface of Mars now is minus 60 Celsius. With some possible exceptions, water no longer is liquid on the surface of Mars. There are two reasons for that. One is that the surface is very cold, and the other is that the atmospheric pressure is very, very low. The average atmospheric pressure is 7 millibars, whereas at sea level on Earth, as you know, the average pressure is 1,000 millibars, one bar. So the combination of the extreme cold and the extremely low pressure means that liquid pure water, is not stable on the surface of Mars. And ice, for example, at the poles of Mars, and there is water ice there, as well as carbon dioxide ice, sublimes. It goes direct from ice, a solid, to gas without passing through a liquid phase. So we can see that once water flowed on the surface of Mars, and when was that once? Well, we can estimate, crudely at least, that it was 3 to 4 billion years ago that water flowed on the surface of Mars. The point here is that, as I mentioned yesterday, all life that we know of requires liquid water at some stage in its life. And therefore, if we're thinking about life on the surface of Mars, as soon as those dry river valleys 3 to 4 billion years old were discovered on the surface of Mars, the focus turned not from looking for extant, current life, to looking for former life. And that was the purpose of the Viking missions of NASA, for example, in the 1970s. So let me remind you what was around on Earth 3 to 4 billion years ago. It was, here we are, we're in this time interval here. We had the stromatolites, remember, built by microbes of some sort. We're not quite sure what sorts of microbes, but all the sorts of things I spoke to you about yesterday. So again, if we use the Earth as our example, and it's the only one we have, then we would predict that maybe there was something similar on the surface of Mars 3 to 4 billion years ago. So the purpose of the early missions to Mars, it started in about 1960 with the pioneer missions of NASA and Phobos missions of the former Soviet Union. The focus there was to look for fossil life, essentially. The Viking missions returned ambiguous results. They had on board them quite sophisticated instruments, gas chromatographs from mass spectrometers to look for organic compounds released from certain experiments that were conducted with the soil, or more correctly called the regolith, on the surface of Mars. And as I say, some of those results were ambiguous, and a few people clung to the idea that there were positive results showing that there are living microbes in the regolith of soil of Mars. However, there are much more feasible chemical explanations for the experimental results. And so that was very, very discouraging at the time. But this image that I showed you yesterday of what the early Earth looked like 3 to 4 billion years ago could equally well be an image of Mars. Everything we know about early Mars now points to the existence of an environment very much like this. Probably not with deep oceans, but possibly with an ocean in the northern hemisphere, for example, relatively shallow one, and certainly, as I mentioned, lots of rivers and lakes, which would have been conducive to life. We know there are volcanoes on Mars, for example. This, in fact, is the largest volcano in the solar system. It's called Olympus Mons. It's 500 kilometres wide Just think about that, 500 kilometres. And 27 kilometres high, 3 times the height of Mount Everest. Who knows where the largest volcano on Earth is? Yes, up back there. Hawaii. Yes, the big island of Hawaii, that's right. Well, this is 3 or 4 times the size of that. So Mars can boast about its big volcano. And just as a digression, I talked about life at high temperatures yesterday. In my view, a good exploration model for looking for life on Mars is to go to former, as they're called, hydrothermal systems, former hot spring systems, like the hot springs that occur in Rotorua in New Zealand or Yellowstone National Park in Montana, for example. And the relevance here is in this volcano, that this caldera, the collapsed structure that I spoke about yesterday, is about the same size as Yellowstone National Park. It's about 70 kilometres in diameter. This would be an ideal place to go to look for, in fact, recent evidence of life on Mars, in my view. It's an interesting place to go to for other reasons. That this cliff around the edge of the volcano is 12 kilometres high. And I always wonder if there are any hang gliding people in my audience when I talk about this. Has anybody been hang gliding? No? Would anyone like to hazard a thought about what it would be like to leap off the 12 kilometre high cliff on Mars? I mean, people do it at a place called Stanwell Tops, just south of here, south of Sydney, near Wollongong. And that's about 300 metres high. This is 12 kilometres high. What do you think would happen if you leapt off the top of this cliff in the hang glider?
Drop like a stone.
You'd drop like a stone. Why would you drop like a stone? Low gravity on Mars. Mars is a smaller planet than Earth. The force of gravity is only about 30 or 40% of us.
Thin atmosphere.
Thin atmosphere, yeah. That's exactly right. So you'd go more or less straight down 12 kilometres. And, of course, your spacesuit would rupture, and when your spacesuit ruptures on Mars, your blood would boil because of the low atmospheric pressure, and you'd blow up. Just a small digression. We have absolutely amazing imagery of Mars now, both from NASA and from ESA, the European Space Agency. The Russians aren't very active in Mars exploration anymore. And this is an ESA image of an area several hundred kilometres wide. And here you see meteorite impact craters on the surface. This is how the age of the ancient river valleys on Mars is estimated, by the number of impact craters on a terrain. And remember we talked yesterday about the impact history of the Earth. We had that curve with lots of impacts early on as the Earth was still accreting and reducing with time. So the same would have been true of Mars. So if you select any particular terrain, like the one we're seeing here, and count the number of craters on it, you can make a very crude estimate of the age of that land surface. And that's how we know that those river valleys on the surface of Mars are 3 to 4 billion years old. But it is very crude. Now, a very intriguing thing was discovered by the high-rise camera that I spoke about, one that's in orbit around Mars at the moment, about 3 or 4 years ago. Here we're looking at little channels on the inside edge of a crater. So here's an escarpment. And these channels are this long one's about 400 metres long. And it's hard to see, but there's a little delta at the end of it. Now you'll notice that there are no impact craters there at all, indicating that this is a very young terrain. And something else that indicates that is that these channels are very sharply incised and have sharp edges. There's no sign of them having been smoothed out by the erosive effects of winds. Even though the atmosphere on Mars is thin, the winds still do move the sediment around, and there are dunes, sand dunes on Mars. So these channels are young enough that they haven't been affected by that erosion. They have no craters on them. It's estimated that they're only well, they're less than 1 million years old, which is blink of an eye for a geologist or an astronomer. Something has flowed on the surface of Mars in the last 1 million years. Now, well, I said liquid water is not stable on the surface of Mars. What on earth could be going on? When these were first discovered a few years ago, people said, well, maybe it was liquid carbon dioxide or liquid something else. But now it is generally accepted that it was indeed liquid water. And I'll come to an explanation for that in a minute. But that is interesting if that is correct, that there is still liquid water able to flow, at least momentarily, on the surface of Mars. We would expect that on Mars that there is liquid water at depth, because the interior of the planet is still warm enough to keep water liquid. And there could be events like a meteorite impact or a bit of tectonic jiggling of the crust of Mars that could release some of that liquid water to the surface, where it could flow momentarily. And I mentioned yesterday that on Earth, at depth is what people call a deep hot biosphere, microbes living down to 10 or 15 kilometres. So we can imagine that on Mars, if there is life, that it could be now living away from the very hostile surface environment in deep aquifers, but could come to the surface every now and then by whatever it is, the sort of event that leads to these channels. So that's a new sort of exploration target for life on Mars that has become apparent just in the last 5 years or less. I said the surface environment of Mars is hostile. It's not only because it's very cold and very dry, at least most of the time, but also there is no ozone shield. There's almost no oxygen in the atmosphere and therefore no ozone. And it's our ozone shield that keeps out the most deleterious wavelengths of ultraviolet radiation. So the surface of Mars is bathed in ultraviolet radiation. There's no magnetosphere to speak of, so cosmic radiation bombards the surface of Mars as well. So all in all, it's a pretty nasty place. And on top of that, what the Viking mission experiments did show is that there is an oxidant of some sort in the regolith, the soil of Mars. Some oxidising compound, partly accounting for the red colour of Mars, the iron oxide red colour of Mars. So not only would any life on the surface of Mars would have to contend with being oxidised, but it would also be zapped by cosmic radiation and ultraviolet radiation. And it would be cold, and there wouldn't be any liquid water. So pretty nasty place. Interesting to speculate about what that means in terms of contamination of Mars from microbes on spacecraft, and we can talk about that if you'd like to. But here we have a glimpse of a hope that there might be a way to explore for subsurface life on Mars. It might come to the surface every now and then. Now, I mentioned at the outset that Mars has seasons, same as the Earth, and that's because it has a similar tilt of its rotational axis to the ecliptic, the plane in which the planets orbit the Sun, as does the Earth. But there's one big difference, and that is that the angle of the axis to the ecliptic varies with time on Mars. Here, that angle is more or less fixed because of the effects of our moon blocking that dynamic system in a stable configuration. Mars doesn't have a big moon. It has two little moons, Phobos and Deimos. They're most probably captured asteroids, and they don't have a powerful enough gravitational effect to make the orbit of Mars stable. So the rotational axis wobbles backwards and forwards on a period of about 10 million years. And the result of that is that what now are icy poles, if the axis was like this, as it was 5 million years ago, and the inclination was 45 degrees instead of 25 as it is now, the poles could melt, and there could have been liquid water on the surface of Mars, on the understanding that solid carbon dioxide would also have evaporated and created a greenhouse effect to warm Mars up a bit as well. So we have a situation where, even though at the present Mars is cold, very cold, it might not have been the same just a few million years ago. And that's the point that's made there. So in thinking about that sort of situation, we have some good modern analogues on Earth of what Mars could have looked like, and a lot of work has been done in Antarctica, in what are called the dry valleys of Antarctica, where the main ice sheet is dammed up behind a mountain range, and there are valleys that just have small lakes which are ice covered for most of the year. That's what Mars could have looked like 5 million years ago, when the inclination of the axis to the ecliptic was much greater than now. So NASA in particular has tested out a number of unmanned vehicles that can look at these lakes and after penetrating the ice can explore the bases, the water in these lakes. We know that in fact there is still quite a lot of near-surface water in the form of ice on Mars, particularly from the results of an orbiting satellite that had a gamma, I'm forgetting the word, spectrometer on board, which was able to measure the abundance of hydrogen in the upper metre or two of the sediments of Mars. And where you see these blue colours, the hydrogen, almost certainly in the form of water ice, is abundant, and where it's red there's not so much hydrogen. There's that big volcano that I showed you before. Here are some other volcanoes. This happens to also be a topographic low that might once have had an ocean in it, and there's evidence of a shoreline along here. So just in the last 5 years, 2 of these sorts of rovers have been sent to Mars by NASA. They're called Spirit and Opportunity. And here you see a very proud group of the engineers, technicians who built Spirit and Opportunity. This is an earlier rover called Sojourner that was on Mars in 1998. Spirit and Opportunity were planned to last about 6 months, but they're still going 5 years later, which is, again, another one of those incredible engineering achievements. These are highly capable rovers with all sorts of instruments on board. They're powered by solar cells. Here are the solar panels. They have a stereo camera on an arm here. They have a alpha particle X-ray spectrometer, which can do some basic elemental analyses. They have a Mossbauer spectrometer that can look at the forms of iron, in particular, redox states of iron on the surface. They have what they call a RAT, a rock abrasion tool for grinding away the outer surface of rocks, so the microscopic imager can look at the inner structure of the rocks and so on. And so we've learned a great deal about Mars in the last few years from these 2 rovers. Early on, they sent back images of Mars like this, and here you see the ripples in the sand. As I mentioned, the wind does blow the sediment around on Mars. The scale here is that these rocks are 1 to 2 metres wide. Now, I don't know whether you can read the names on these rocks, but they're intriguing. This rock, just imagine, you're at the Jet Propulsion Laboratory in Pasadena, and day after day, night after night, you're dealing with a huge flood of data coming back and lots of images. What do you do to amuse yourself? You give rocks names. So this rock was called Warrawoona, and this one was called Fortescue. And if we look here, this one's called Wallaby. This is the shadow of the rover. This one's called Pilbara. Starting to see a pattern. This one's called Hammersley. This one's called Jackaroo. Many of you may not know what a jackaroo is. It's a cowboy in Australian parlance, essentially. What this indicates is the role that Australia plays in having analogues of places on Mars that are interesting to explore. So both NASA and ESA scientists are particularly interested in places like the Pilbara as places to think about when they're exploring for life on Mars. And so I guess one long night they were thinking about the Pilbara, and they tried to remember names of places in the Pilbara. They could remember Wallaby, that's not so hard. There are a few outliers here. Kimberley's, well, that's 1,000 kilometres from the Pilbara, but let's not be fussy. Wheelie Wally is actually a name in the Pilbara. And so there you go, there's the link between Australia and Mars. This shows you the driving track of one of those rovers. It took 91 days, or days on Mars are called sols. No idea what the Martians call them, but that's what we call them, sols, after the sun. So it took 91 Martian days, and they're about the same length as an Earth day, to drive from where it landed to there. And you see the scale here, 100 metres. It's only a few hundred metres. It's pretty slow going on Mars. They're still limping along. And they saw things like this. And if this was Earth, you'd say this is a typical layered sediment, just the sort of thing you'd expect to form in a lake or in a sea. And if you look more closely at some of those layers, which they did, they noticed all these little black spots. And the black spots turned out to be little spheres. And with the analytical instruments aboard the rovers, I could find out the composition of those spheres, and they're iron oxide, they're Fe2O3. What they are is, geologists call them concretions, little precipitates of iron oxide that precipitated from water in the regolith of Mars, the soil. And you notice here there are all these hollows. These are places where crystals of soluble salts have been dissolved away. Well, firstly, the soluble salts precipitated from water, and then in a later phase, more water dissolved them away. So there is evidence of an active hydrological cycle on the surface of Mars when these particular sediments were deposited, which was probably 1 to 2 billion years ago. So we keep finding evidence of liquid water on the surface of Mars, which keeps encouraging us to think that there not only might have been life there once, but there could still be life. And just to give you an impression of the sorts of clever things that are being done by those instruments on the two rovers, here are some results from the alpha proton X-ray spectrometer, and you can, well, see there's calcium and titanium and chromium and iron and so on. And from the Mossback spectrometer, it can be seen that there's ferric iron and ferrous iron, and in fact even some minerals like this silicate can be identified with the Mossback spectrometer at this place, the Gusev crater, in 2004. So it's pretty clever stuff. Now, I mentioned the Phoenix lander in one of the first images I showed you. I showed where it landed near the North Pole. And the purpose of this lander was to look at the environment near the North Pole to see if it might be conducive to life. And this is what the Phoenix lander is like. It was a static lander, not a rover, with solar panels. And here's the instrument package. And you can see the scale there with the people standing next to it. It's a pretty big thing. Now that clever camera, a high-rise camera on the Mars Reconnaissance Orbiter, actually managed to photograph the Phoenix lander as it was passing through the atmosphere. There's the lander and there's its parachute. Pretty nifty to have managed to point the camera in exactly the right direction, that there's something descending at a high rate through the atmosphere of Mars. And then after it had landed, the high-rise camera actually was able to see the lander, there it is, well, there is a high resolution. You can see it's pixelated there, but remember each of those pixels is about 25, 26 centimetres. And there's the heat shield, and there's the parachute. And it dug into the regolith, and it uncovered this white material in the regolith, and that sublimed. Some of it sublimed over a period of a few weeks. The lander was operating, and it sublimed at measured temperatures, indicating that it was indeed water ice, quite close to the surface. So that this is a weather measurement from the lander on one day, Sol 1. Here we go. The pressure was 7.85 millibars. The wind speed, 14.4 kilometres an hour. Very clear, good visibility. The average minimum temperature was minus 79 centigrade, average maximum minus 30. The temperature at the equator, by the way, gets up to about plus 17 during the summer. And a curious thing was discovered. The camera on Phoenix looked at the legs of the lander and saw all these little patches, the little globular patches that disappeared over time. And they've now been interpreted as liquid water. And here we go again. Liquid water on the surface of Mars now. It's impossible, but it seems to be true. Well, the analytical instruments aboard Phoenix discovered that there is a lot of perchlorate in the regolith. It's not known what the full composition of the perchlorate is, but there's perchlorate. It's ClO4 radical. And it turns out that if you have perchlorates at high concentration in water, it lowers the freezing point of water down to about, I think, can take it down to minus 50 or so. So it seems that the water at this site has antifreeze in it. And that could be one explanation for those little gullies that I showed you on the surface of Mars before. The water could be brine, very salty brine. And the instruments, the so-called LIDAR, which is equivalent to radar but using wavelengths of light to look at the atmosphere, saw snow clouds and snow falling. First time that had been observed on Mars. So again, we get the picture of an active hydrological cycle, still active on Mars. One of the most remarkable things that's been found in the last few years is shown here. This is a map of the concentration of methane in the atmosphere of Mars. So we're looking at half the planet here, and red is high concentration. There are parts per billion on the scale. Now, methane would be photodissociated in the atmosphere of Mars in a matter of days by ultraviolet radiation. And the fact that there's still patches of quite concentrated methane in the atmosphere of Mars means that there must be an active source of methane currently on the planet. Now, on Earth, there are two ways that methane is released into the atmosphere. Anyone know what they are? We do get methane in our atmosphere in low concentrations. Where does it come from? Yes? Volcanoes and microbes. That's right. Well, geological processes, chemical processes in volcanoes and in hot springs produce methane. And there are microbes, and I mentioned to you yesterday actually, called methanogens that produce methane. These occur in the guts of cows with results that I won't speak about. Yes, I'm reminded of all sorts of undergraduate jokes. So this is very intriguing. It tells us again that there's something active happening in Mars too. It used to be thought of as a dead planet. It might have been interesting and active 3 or 4 billion years ago, but it's dead, nothing happening there at the moment. Well, there is something happening. And it could be biological. this is the most powerful evidence we have at the moment that there could be microbes on Mars. But it's equally likely that it's evidence of a geological process. So that's where we stand at the moment. One way to tell the difference between methane produced by, say, volcanoes and that produced by microbes is to look at the carbon isotopic composition. As in photosynthesis, for example, as I mentioned yesterday, carbon-12 is selected over carbon-13 in biological processes, and so if this is biological methane in the atmosphere of Mars, it may well have a signature in the form of its carbon isotopic composition. But that has not yet been measured for this methane, but it will be measured in the next few years. And should it turn out to have a high concentration of carbon-12, then we would have very intriguing potential evidence of the present life on Mars. So that's something that might happen within the next 5 years. Now, all the missions to Mars have been one way. There has never been a two-way mission to Mars. So these probes go there, the satellites, the landers, the rovers, they're all one way. We've never brought anything back from Mars. There are now quite advanced plans for what's called a sample return mission, and I'll talk to you about that to some extent now. Now, it's going to be very complicated, and it will require 2 launches on very large rockets. The size of the rockets that we used in the Apollo days, huge rockets if you've ever seen these, and there'll be 2 separate launches with different components of the mission. So that'll all have to be coordinated. And this is what their so-called mission architecture looks like. I don't want to go through this in detail, just to give you an impression of how complicated this is. And it is doubly complicated because it's going to be so expensive, if it happens, probably around about $40 billion, that it'll be an international mission, particularly involving NASA and the European Space Agency, ESA. So you have to get NASA and ESA working together to start with, all talking the same language and not using imperial units on one hand and metric units on the other. Plenty of scope for confusion and discussion. So that all has to come together. Then we have to have these 2 launches. One is probably going to be an Ariane rocket from ESA, and the other is a rocket yet to be built from NASA. And you send up a lander that will, or maybe several small landers that will travel around and go to pre-selected places and take samples. Now bring all those samples back to a central location, load them aboard a launch craft on the surface of Mars, which will have to have been sent on one of these rockets and will have to have landed safely on Mars. And then that craft will be launched, and it will rendezvous with a return craft that will be in orbit around Mars, and that return craft will then come back to the Earth, and will have to safely land back on the Earth. So that's what you get for $40 billion. And all that to bring back probably less than 1 kilogram of sample, because that's the way the metrics work. I forget how many tons go out, but it's hundreds and hundreds of tons that launch from Earth, and less than 1 kilogram of sample ends up coming back. So it better be the right kilogram. But the advantage over just looking at meteorites from Mars is that we'll know exactly where the components of that 1 kilogram come from. So we'll have context. And context is missing with the meteorites. And a lot of what we do when we look for early life on Earth is to make geological maps and understand the history of the rocks and understand exactly the context of our samples. This is going to be the first opportunity to have context for samples from Mars, and will greatly increase the chance of finding life on Mars. Before this mission, there will be 2 launched in 2011 and 2013, one NASA, one ESA, which will land 2 large laboratories on the surface of Mars. These are about the size of average four-wheel drive bush vehicle. They're big laboratories, highly capable. That will happen, almost certainly. Whether this sample return mission happens is another matter. It's being assumed that it will, and the planning is already advanced. One of the issues is the issue of bringing samples back to Earth, and what if they have some sort of dangerous microbes in them? So there's going to have to be a sample return facility. Microbiologists call them PC labs. And on Earth, there's a grading of PC1 where nothing much dangerous is put in there, up to about PC5 where you have extremely dangerous viruses and the like Ebola virus and so on. But this is going to have to be a PC6 laboratory, and the question is who's going to have access to the samples and all the rest of it. So that takes a long time to work out, and is being worked out at the moment. The time frame for all of this, there are several candidate timelines, as the mission planners say, but the point is that the launch is not going to be before 2018 at the earliest, and the whole process of getting there and assembling all the components of the mission and getting back again means that some of these missions won't have samples back on Earth until 2025. I'm afraid it could just be too late for me. But maybe not, I might be around when these samples come back. You will all be around, I hope. And this is your best chance to discover whether there's life anywhere else in the universe when these samples come back in the 2020s. I think there's quite a high probability that there is life on Mars. I think it's almost inevitable, in fact. And the reason I think that is because, as I mentioned to you, we have meteorites from Mars. Well, Mars will also have meteorites from Earth, and that means there's a traffic. There would have been a traffic of rocks between Earth and Mars over billions of years. Rocks on Earth contain microbes, and the ejection physics are such that some of the rocks that are ejected are not stressed particularly, nor are they heated particularly, so microbes could survive ejection from one planet and get to another planet and seed that planet. In fact, life might have started on Mars before here, and we might have been seeded by Martian microbes, and we might be all Martians. Perfectly respectable scientific hypothesis. And if you look around, you might feel it's quite reasonable. Especially if you look at me. Why does it matter? Well, everything we know about life on Earth is based on a sample of one. Now just think about it. This is literally true. We have a sample of one. All our generalisations about biochemistry, about medicine, are based on what we know from this sample of one, life on Earth. That's not a very good way to do science, to make predictions based on a sample of one. What if we found another sample of life on Mars or anywhere else, in that respect, that we could demonstrate had a separate genesis, a separate origin? And we had not just one sample of life in the universe, we had two. Just imagine the consequences of that. Think about it. Things that we might have thought were key components of life, like the need for liquid water, like the need for DNA or RNA as genetic molecules, for example, or even the assumption that all life is carbon-based. All of those assumptions might be overturned. With the return of samples in 2020, it could be shown to have life that arose separately from life on Earth. That's why I think, in an intellectual sense, this is worth doing, and why I don't mind spending a few dollars of my taxpayers' money every year. Remember I said the simple missions to Mars cost about $260 million a year. Well, if you're a US citizen, that's only $1 each per year. It's pretty cheap. If you're exploring such profound questions as whether we're alone in the universe, well worth every cent, I'd say. Thank you.
Okay, any questions? Well, let's start over there. So now how